I'm excited today to talk to you about the autoionization of water because, first of all, it's a great vocabulary term, and second of all, it's the foundation of pH and kind of everything we know about measuring how concentrated acids and bases are. So the pH scale is really important to our understanding of acids and bases, and you probably learn about pH before you even really understand what acids and bases are from a chemical kind of standpoint, because we have papers that show us what colors changes are, and those color changes respond to different concentrations of things, and then those different concentrations can spit out a number, and that number, that pH value, tells us where it is on some scale and whether or not that's good. So, we can pH test our wells or our swimming pools or our fish tanks, etc. So that all comes about because of the autoionization of water. That's how we built the pH scale. And it kind of comes from one of the great lies that we tell you in chemistry. So autoionization in and of itself is just two of the same molecule that react together and form ions. So that seems kind of weird, because if I react two of the same things together, you wouldn't think they'd do anything, right? But water is a special thing. And so the water is one of my favorite chemicals. I get really excited about water. And one of the many reasons I love water is because of this interesting and weird behavior, this autoionization behavior. So water, and this is kind of a cool feature, is the most common acid in the world. And by definition, an acid is something that donates hydrogen. It's got hydrogen to give. It's happily donating it. It forms hydroxide. It's also the most common base in the world. So water can accept a hydrogen, right? If we kind of think about this guy is donating and this one is accepting, although it doesn't matter which one is which, then this one that accepted the hydrogen forms hydronium, and this one that gave up the hydrogen forms hydroxide. So we have this kind of amphiprotic substance or amphoteric substance that can act as either an acid or a base. And when it is in just hanging out with itself in any glass of water, so I'm drinking a glass of water right now, in my water there's a small amount of hydronium and hydroxide. So when we tell you that pure water doesn't conduct electricity because it doesn't have ions in it, yeah, sorry, it does. It does have ions in it. It has hydronium and hydroxide, but in pretty small quantities. Now let's think about this in terms of equilibrium, because this is definitely a reversible reaction. Because while water does this behavior, it still really likes to be water. Water is so happy being water, and we've talked about this in past videos with how attracted it is to itself, how cohesive it is to itself, because of various things like hydrogen bonding, right? Like it causes it to stick together really well. And water just really is all about water. So the equilibrium constant for this reaction, so my glass of water is at a certain temperature going to reach equilibrium, let's say 25 degrees Celsius. My apartment is definitely not that warm right now, but if it was at 25 degrees Celsius, then the equilibrium constant that governs that is equal to 1.0 times 10 to the negative 14th. And this is kind of a magic number for water, and we'll talk about why in a second. Okay, so let's think about this equilibrium. Products over reactants, if we're thinking about this in terms of concentration or KEQ, either way. So this is going to be the concentration of my hydronium ion times the concentration of my hydroxide ion raised to their powers, which in this case is 1 and 1, over my waters, but I'm not going to include the waters. Why? Well, I'm not going to because it's a liquid. It's a pure liquid. So these pure liquids are not going to be involved. So my K value is equal to this, and actually we give it its own equilibrium constant. That is how special water is. We call this KW. W for water. That'd be funny if it wasn't for water. That would be so like chemists to fool you like that. But in this case, it actually makes sense. Okay, so what does the magnitude of this number tell us then? If we're thinking about this in terms of equilibrium, because we always are because we're chemists, then this number is very tiny. So that means the concentration of my products is very tiny. So that means that in general, this reaction heavily favors the reactants, right? It doesn't necessarily like to do this. So even though there are some ions in solution, it happens, there's some in there, then it's not going to be a lot of them, right? And if we think about this in the reverse, so if I'm looking at the reverse reaction, or if I flip this thing around and I'm thinking, how badly do these guys want to form water? And I took the inverse of this, right? Because when I flip a reaction, we know that we take the inverse of this because now it's products over reactants. So 1 over this would give me 10 to the 14, positive 14. So that's a huge number, which means that in general, it really wants to drive towards those water molecules. So water likes to be water. But in the meantime, it also does these kind of crazy side things, and that allows for some interesting behavior. And this Kw, this kind of magic equilibrium constant for water, is how we build our entire pH scale. So let's talk about how that works. And we're going to do that by an icebox. So here's my icebox for this. We're going to ignore these guys because they're water, pure liquids. So we're going to ignore them. So if I think about my icebox here, and I say I'm putting water together and I'm allowing it to autoionize, so I don't have any of these guys to start off with. My change is going to be positive X here, right? I'm adding products here, so it's changing by a molar quantity. So if we were thinking about, if we had anything on this side we could talk about the concentration of, we'd say it's a negative X plus X plus X, which gives me an X for each of my equilibrium concentrations, which means that I have the same equilibrium concentration of my hydronium and my hydroxide under kind of normal conditions. Now if we do this, here's my Kw again, 1.0 times 10 to the negative 14th is equal to my concentration of hydronium times my concentration of hydroxide. Then that's going to be equal to X times X, or X squared. So X squared is equal to my Kw. So if I take the square root of both sides, then I end up with X is equal to plus or minus 1.0 times 10 to the negative 7th. But we know that it can't be negative because it's a concentration, right? My numbers have meaning, so even though mathematically I can have a negative number, it represents a physical quantity, which is a concentration. So that means that my X is equal to this. So this is my concentration of both of my hydronium and my hydroxide at equilibrium. All right, now, what does that mean? Well, if I think about taking the logarithm of this, so if I take a negative logarithm of this quantity, 0.0 times 10 to the negative 7th, then mathematically we would say we're taking the power of the hydrogen, or we're taking the potential of my hydronium, or the potential of my hydroxide, or the power of my hydrogen, however you want to think about all that. So a negative log in math is a lowercase p, right? P for power or potential. This is the concentration of my hydronium, or my hydrogen ions, right? So this is going to give me my pH. When I take the negative log of this concentration, I get 7, which is why our whole pH scale is built around water, because 7 is a neutral pH. It's right in the middle. And so this 14, this 10 to the negative 14, gives me the boundary of the edge of my pH scale. So it's a 14-point scale, and it's based on this calculation where the pH is equal to the negative log of the concentration of hydrogen ions. Or you could say the negative log of the hydronium ions. It's the same number. So pH again stands for power of hydrogen. I like it that way. But it also means potential of hydrogen. You'll see it that way too. I think that's actually more correct, but I like power of hydrogen. It's the potential. It's got great potential. So this is my calculation for pH, and when I take the negative log of the concentration, then it gives me some value. That value then sits me on the scale somewhere. So this pH scale goes somewhere between 0 and 14. Now we like to use this as the boundary because this is water at 25 degrees Celsius, so it kind of gives us this nice range. That is not to say that I can't have negative pH values, and I can, and it's not to say that I can't have greater than 14 pH values, which I also can. So this is just the scale for most things that we run into, at least on our planet in this great big universe. So the pH scale works well for us because we're so built around water. Okay, so low numbers then are acidic, high numbers are basic, right in the middle is neutral, and neutral is built around that icebox that we just did for the concentration of my hydrogen ions, the power of my hydrogen. Just to give you a general sense, kind of on the pH scale on the low side, at a 0 would be something like battery acid, which is a combination of acids that allows for the flow of electrons and allows for batteries to do their thing. Lemon juice sits at about a 2, as does stomach acid. Lemon juice. Kind of depends on how dilute the lemon juice is. Lemonade obviously would be a little bit less acidic, kind of further up the pH scale. Milk is about a 6. That always surprises people. You want milk to be basic, right? Because when we drink milk, then it helps to neutralize your acidic stomach, but it's really just more basic relative to your stomach acid, right? It's quite a bit more basic. Our blood sits at around a 7. Our saliva sits slightly on the more acidic side, which makes sense because the saliva is kind of the first step in our gastrointestinal breaking down the food, so it makes sense that it's slightly acidic. So our blood's at about 7. Ammonia, which is a household cleaner, is around 12. So ammonia is kind of one of the primary components in things like Windex, so it's a weak base, and it sits at about a 12. Lye, or caustic acid, or sodium hydroxide, sits at about a 14 when it's at its most concentrated. You can have different concentrations of sodium hydroxide, but in its concentrated form, it is definitely on the basic side. Okay, so that's our pH scale. We can use it to find different household items. You know, our indicators can give us different color changes, right? Things like pH paper or universal indicator paper, litmus paper. Different indicators like red cabbage solution is one that you can make at home. A lot of things naturally will indicate different pH levels that are plants and fruits and leaves and all sorts of things will give you pH indicators, which is kind of fun. Okay, so there's our scale. Let's do an example of a calculation then. So if I have some orange juice and I have a concentration of hydrogen in there of 2.9 times 10 to the negative 4, then my pH is equal to the negative log of that concentration. So that's 2.9 times 10 to the negative 4. And that's going to give me a value of 3.454 here. Okay, so 3.54 from my pH scale, we know that this is acidic, right? And that makes sense because citrus in general is on the acidic side. It has citric acid in it as one of the primary acids that causes that. And so 3.54, fairly acidic. I want to note here about significant figures. So my concentration has 2 sig figs, and so does my answer, even though it looks like I have 3 sig figs. So this is something that always frustrates students, because with logarithms we have different rules. We're no longer adding and subtracting or multiplying and dividing. So for sig figs for logarithms, it's all about the number of decimal places. So these decimal places here give me 2 sig figs as well. So I look at 3.54, and now I go against every rule I've ever taught you, and now we have 2 sig figs in that thing. So it's just a quirky thing about logarithmic calculations. All right, so that's pH. A little bit about the pH scale, kind of where it comes from, which is the autoionization of water. And we'll talk more and do more calculations with pH and then pOH in future videos. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.